All right, so we welcome everyone to our seminar of mathematical physics, and our speaker today is our hometown boy, Svatopluk Krýsl, a researcher from Charles University, and he's going to tell us about quantization defined by symplectic spinors and the deRham sequence tensored by these. So, over here.
deRham. Thank you for the introduction. It's a pleasure to speak in front of the audience I'm familiar with. So to the audience. So the topic is was mentioned. My motivation is actually analysis analysis of the.
Sorry, I just realized that I haven't. I probably should share this. But yeah, sorry. Please go on. I can do this.
It's analysis on vector valued functions on manifolds, like deRham operators, nature operators, Dirac operators, and to generalize them to analysis of functions with those values in vector spaces, but these vector spaces are infinite dimensional. So there are examples, not so many of such of operators which can be analyzed. Namely, the Dirac operator introduced by Katarina Haberman, then deRham complex twisted by symplectic spinors, which we will speak about, and possible subcomplexes, but maybe more general abstract operators that can be defined as elliptic and further examples. So motivation is basically Hodge theory, generalized Hodge theory for vector bundles, two vector bundles of infinite dimension. Next motivation is quantization. So first, in the simplest way, I will say very precisely, but let us suppose that we have a symplectic manifold, and we would like to find a non-zero homomorphism of the Lie algebra of smooth functions on the manifold, equipped with the Lie bracket given by the Poisson bracket into the space of endomorphisms of a Hilbert space, equipped with the commutator of maps on Hilbert space. So this depends on what are endomorphisms, whether we consider only bounded endomorphisms, and what this map shall be, whether it shall be continuous. This map to be a quantization shall certainly be a Lie group homomorphism. So these are Lie algebra homomorphism. So these are Lie algebra, so we need non-zero Lie algebra homomorphism. Content. We will speak about the symplectic spinors. They are developed via the so-called metaplectic representation we will introduce. Then we will speak about this geometric quantization possibility. And then we shall go into giving some examples of this infinite dimensional vector bundles and operators on them, which can be defined in a geometric, let's say, geometric way. And then we will actually prove or show that the Dirac operators, further operators in this infinite dimensional setting can be found in deRham sequence twisted or tensored by the symplectic spinors, which are carrier of the metaplectic representation, the vector space carrier. So I shall distinguish tensoring and twisting. I will try. Tensoring shall really mean taking tensor products, and twisting shall be explained in a moment.
Yes, sorry. I think
I worked. No.
And can you try it now? It works.
Yeah. So basic setup is symplectic geometry flat model vector space. V, a real symplectic vector space of dimension 2n for definiteness. G, the symmetric group of this vector space, all linear maps preserving this omega in the symplectic form in this way. This is the symplectic group, it is a non-compact symplectic group. Then let us consider the Heisenberg group. which is not such a canonical choice as above, because we shall fix the field, real field here really. So let's consider the Cartesian product of V and the field R, scalars R. This is isomorphic by with R to n plus 1 when V is two-dimensional. Then multiplication on this space, this set, is introduced in this way. We take sum of the first coordinates of the vector space. We add these scalars, which are sometimes considered as time variables. And then we add half of the symplectic form in which we plugged V and W. So neutral element is 0, 0. Inverse is given by this. This can be checked directly. So I get this 1/2 is only by convention. Center, it can be calculated easily that only this time variable is the center. Then let us take something which is let us take a so-called symplectic basis. This is a two-tuple of vectors which satisfies certain technical condition given by omega 0. So EI's plugged into omega 0 with 0, EI's plugged into omega 0 with 0 as well, and EI and BI plugged into omega is canonical delta. Okay. EI, BI plugged into omega 0 is 1. And other possibilities are 0. Plugging AI, BJ is 0 if and only if E is not J. E is not J, for example. I'm not speaking about plugging first BI and then EI, but it should be consistent. It should give the negative of plugging EI, BI first. So this is a symplectic. This is one possibility of symplectic basis. There are more notions. There are at least 3 used to define the notion of symplectic basis. It's not like in Riemannian geometry. So, with respect to the symplectic basis, omega has a shape of an anti-block diagonal matrix with block 0, -1, 1, 0. So this is a technical thing. And let us consider 2 subspaces. The first is spanned by the first set of AIs, by the set of AIs, and the second by BIs. They can be checked to be maximal isotropic, EI plugged into omega 0, BI as well. And now we define the orthogonal, actually the scalar product, by declaring this basis to be orthogonal. This symplectic basis. So there are also further notions of symplectic basis for which the matrix omega 0 has this shape. So I don't want to bother you with details. This space. Has this form, sorry. Okay, so we can, if it's everything all right, we can continue there. So just maybe I'll find out. What was not maybe too easy to understand. Okay. So no, we shall represent, we have vector space V, Heisenberg group V times R, and we will represent this group by so-called Schrödinger representation. This is quite known within harmonic analysis. We represent the Heisenberg group, so we shall give a homomorphism of the Heisenberg group into the group of unitary, we represent it unitarily, into the group of unitary maps of L2 functions of this, for example, second Lagrangian subspace of this span of BIs. Yeah, so I didn't say it's Lagrangian subspace. And we represent it as follows. Representation takes element of this Heisenberg group, evaluates it on a function, and we shall get a function again from L2. And we do it in this way that we change the argument of the function by V double prime, when V double prime is the second coordinate of V, when this V is considered as a direct sum of L prime, L prime, prime. So don't forget that V is a direct sum of L prime, L prime, L double prime. Yes, because it is kind of disjoint sets of the bases, subsets of the bases, which give by union the whole basis. So we represent it in this way, and we multiply it by this. It's not Gaussian, by some wave function. Say, okay, using the scalar product and the spans of this V in the Heisenberg. So this is a prescription. Why this strange representation? If we differentiate it, we get canonical relations from quantum mechanics. If we differentiate it with respect to V prime, we get either multiplication by V prime or differentiation with respect to prime. And if we differentiate it with respect to double prime, we get either differentiation with respect to double prime or multiplication with double prime. So this reminds you to the Schrödinger canonical relation, Heisenberg canonical relation. This representation is unitary. This is somehow easy. Translation doesn't change the L2 norm of the function, and multiplication by number on a circle also don't. So the norm of f is same as the norm of the result. So the mat is unitary. You think about it, not as a homomorphism. Centers is 0 times scalars is represented only by this minus IT. I'm checking 0, 0, 0. Okay. So this works. And now we would like to construct the symplectic Diracs and the metaplectic representation. So one possibility is to consider a whole family of Schrödinger representations by so-called twisting. Why? Why twisting from, let me say, maybe my hypothesis from a physical side, why to do this? Physicists in 30s, as far as I know, wanted to prove that the canonical quantization, not only the relation, but the canonical quantization, is basically unique. So they wondered whether there is no further representation such that it can give some similar relation. Let us say it only briefly and precisely in this way. So the easiest way is try to twist the Schrödinger and find out what happens, but no surprise will come. Yeah, so this will be really equivalent. But let us do it for the point of view of mathematics. So automorphism of Heisenberg group. Just take A from symplectic group, multiply the vector part of the Heisenberg group, and say this is the action of the symplectic group. It is a group automorphism. It can be checked. It preserves the center pointwise, and moreover, it satisfies this relation. So then, what? It means actually this tau is a representation, and thus it induces a left action of this Hn into Hn. Then, so this tau I is a representation. Thus, it is a homomorphism. Okay. Regardless whether it is a homomorphism or not, we can compose it with a Schrödinger representation. Just formally, tau I goes from Heisenberg into Heisenberg. Schrödinger representations go from Heisenberg into unitary transformations of some Hilbert space L2 function. So this can be done, and moreover, it must be a representation since both are homomorphisms. This is the so-called homomorphism. Yes, it is a homomorphism, but it is not only homomorphism with respect to A, but it is also a homomorphism with respect that it is a homomorphism of the Heisenberg group. It is even an automorphism of the Heisenberg group. Yeah, so this is automorphism of Heisenberg for any A. This can be checked by just this is actually only associativity of multiplying with matrices or just putting on these ABs. So in this way, for each A, yeah, tau I for each A automorphism of Heisenberg, for each A, we get a representation that we call twisted Schrödinger representation, and we get a whole family of such representations. But there is also normal theorem which was connected to the question whether the quantization is unique. Each irreducible unitary representation of the Heisenberg group, so the basic physical variables which we may think of as P and Q and T, on a separable Hilbert space, denoted H here. Such that the center acts by this number, I must say, necessarily non-trivial. This is non-trivial. The T is a variable. So for T, it acts by multiplying by e to the power minus it times identity for each. So the action is T goes into e to the minus it. So this is non-trivial. Such a representation is always unitarily equivalent to the Schrödinger representation. The problem theoretically would be here when here was 0, and it would act as identity. Then it wouldn't be. So from physical point of view, there is some constant, sometimes written Planck trans, which is non-zero. And so this is really non-trivial. Nice proof. So this goes back to Stone-Neumann. But nice proofs are in Dietmar-Echterhoff, a bit abstract, and in Fallout there is a, let's say, hand-made proof by Weiss and Wigner-Parkman transform by some specific wave packets, which we won't Chirpat's problem, which we won't go into. It's simpler. So this is more constructive and this is more abstract. Let us say it in this way. And now what we can do. We have the family of Schrödinger representation, the twisted Schrödinger representations. And but this says that they are all unitary. It's easy to see. This says that they all must be equivalent to the original Schrödinger representation for each A. So we have a bunch of such representations, Ri. We have this one, and they must be equivalent. Okay. So equivalent, what does it mean? So we have intertwiners, G-equivariant maps, morphisms of representations, continuous G-model homomorphisms. So let us denote them by UI for each UA. For each A, we consider this. And we say that UA intertwins R and RA, so everybody knows it. Here. Okay, and now we will go.
The first one that one Echterhoff differs from the Stone-Neumann proofs original, or
A bit. I don't know exactly. A bit. By this, okay, so we have these intertwiners between twisted representation and original. And now we do it for the twist representation twisted not only by A, but by AB, by tau AB. UAB, by definition, intertwins R and RAB. It's the definition of UA and intertwin. So I was asked to speak about a bit about the representation, so I do it. So it's only maybe the only proof we will mention. For VT in the high symplectic group and a symplectic map, symplectic element, we can compute this. RAB, UA, UB. These are these intertwiners. RAB is composition with tau B. Tau B is plugging in B. So we plug in B. Right, UA, UB. What is RA? RA, we know that it is equivalent to the Schrödinger representation, which we said before. And what further? This cancels. Then we have this, and we again use the intertwiners. Not the definition of twisting that it is twisted, but the V would be a circle of ideas. So we do this. UAUB. UAUB is actually this. RBVT is UB, RBT, UB minus 1. And we just write this. So no UB and UB minus 1 cancel. And UAUB becomes on the left-hand side. So UAUB is also intertwiner of this twisted representation and this twisted representations. Thus, we have two intertwiners. This one, by definition, UAB intertwines R and RAB, and then we have UA composition UB. And now there is a sure lemma for unitary representations on Hilbert space, and we know that these two intertwiners must be multiples, which is nice. And since they are unitary, they must be multiples by circle number. So we call that circle number. Unit, complex unit. So let's say complex unit. Consequently, and this is the definition, UAB being possible to write in this way, the so-called projective representation of the symplectic group. This is true representation would be, so everybody knows when this C would be 1. But then there were two people, at least, who were able to use this fact to define a representation of the double cover of the symplectic group. One was André Weil, who was searching for symmetries of theta functions, and second was David Shale. And he was, as far as I know, searching for quantization of solutions of the Klein-Gordon equation. So it's a very different approach. This Weil paper appeared in Acta Mathematica. Shale appeared in Transactions of American Mathematical Society in a quite similar period. Okay. And they found that it is possible to lift these intertwiners, which do what? They take A and they give you intertwiner on the Hilbert space L2L double prime. Let's say that L2 double prime is no L on vector notational reasons. They were able to say that these UIs lift to the double cover only of the symplectic group. The symplectic group has a connected double cover. Basically because it contains a circle and contains unitary group. And the unitary group, not special unitary, but unitary group, and it contains circle, which can be double covered. So connected in a connected way.
But it's not the universal cover, it's just the double cover.
No. So let us denote this double cover by a lambda and the double cover itself by G tilde. The double cover is called the metaplectic group. And now we just recall that we have symplectic symmetries of the vector space. It is known that it is not embeddable into any GLRN in a continuous way for any finite n. So it's a non-matrix group. Okay, so the lift of the intertwiners was denoted by U tilde, and now we denote it by rho only. I don't know why. We change the notation. It's easy. Now this double tilde, this row representation, this is the metaplectic representation. So that is a unitary representation of the double cover of the symplectic group. Sometimes it is called oscillator, Shewile, symplectic spinor, Segal Shewile. So it has many names. Elements of these unitaries are called symplectic spinors. Can be called symplectic spinors. So it's quite interesting representation by intertwiners, and there is a luck that we can take only double cover and not more folded cover. So one shall compute cocycle conditions for the CAB and show that one can make it really a cocycle for which the appropriate cohomology vanishes. Okay. So another picture, yeah? So when they are analysts, they maybe don't like L2L. So there's Bargmann-Fock space picture. So now we just speak about L2L, about square integrable functions on some Lagrangian space of Rn. And this is quite interesting that we can get a Hilbert space. So V is again this two-dimensional symplectic vector space, just a vector space. And we consider holomorphic functions which have definite integral, finite integral, when they are multiplied by this weight. This norm is induced by the bracket. So this is actually multiplied by the Gaussian. Let's say Gaussian. Say. So holomorphic functions such that this integral is finite. Holomorphic, what does it mean? On V, we choose a complex structure which is compatible. Complex means this. Compatible means symplectic mat, like it preserves omega 0. And the induced bilinear form, G0, is positive definite. I maybe should write what it is because geometry is not collective geometry is not really known. So let us take, for example, this. We take G0 and we say it is compatible if this is positive definite. So we have G0. We have G0 to, this is a complex structure on C. This is multiplication by I, basically, rotation counterclockwise. And we know what is holomorphic. Holomorphic means that differential, the classical real differential of this function, taking the real and imaginary values, intertwines these complex structures. So it is complex linear. We say that the differential is complex linear. This is a reformulation of the Cauchy-Riemann equations in more dimensions. And no, maybe Cauchy-Riemann relations, which say that the total differential is complex linear, the total differential of the function. And we can say it in this way. Fix a classical complex structure here, fix a compatible complex structure here, and we say this is holomorphic. And when we're writing this equation, one can find log diagonal Cauchy-Riemann. One can find analogies of Cauchy-Riemann. Okay. Now, this Bargmann-Fock space is a Hilbert space. This is quite interesting. This is a Hilbert space. It's the window. Yeah, and it contains all polynomials, for example. It's nice. Polynomials can be multiplied by exponential with finite integral. So this is a Hilbert space. We can decompose it with respect to the metaplectic representation, which we somehow transplant on it. Each Hilbert space of countable infinite dimension is isomorphic to any other Hilbert space of countable infinite dimension. So this L2L must be isomorphic to this, and we just take the declare this equivalent, its map unitary equivalence to be the intertwiner, and we get a representation of the metaplectic group, the double cover of the symplectic group. Now we can take smaller spaces. So now we require, yes, FB in this Barkman form. It shall be integrable in this way with this exponential, but it shall be integrable also if we multiply it by some polynomial, even that. So we get something smaller, a smaller space, and we take a intersection of these spaces. And this appears to be the space of smooth vectors of the metaplectic representation. It means that one can differentiate the representation on it. So not in infinite dimension, not any vector can be differentiated. We need this. This exists. Or the function in the space denoted by sorry. In the function minus, right? I don't know. And here shall be so if the function has a property that this differentiation exists for any v and any x from the finite dimensional Lie algebra, the symplectic or metaplectic group, then this must exist. And it can be shown, can be written probably easier, but it can be shown that the space of such functions that the differentiation exists is precisely this intersection space. Then we can take so-called k-finite smooth vector. These are functions from this space for which the k-orbit by the metaplectic representation, has finite dimensional span. And this is even smaller. This is actually, this denotes symmetric power. And this W is a vector space Cn, nothing but else. It can be defined invariantly in this way.
Sorry, what is capital K?
This is small k.
But there is a capital K at the end of the line.
Yeah, k, actually k finite. So in representation theory, one knows that k finite denotes the maximal compact subgroup of the metaplectic group.
Okay.
Which is the double cover of the unitary group. So I can search for smooth vectors, or I can search for, it's easier, the formula. And this is the space of k-finite vectors. This is a Fock space, yeah? So we have really polynomials of symmetric powers, which you know from quantum physics. So, remarkable properties of metaplectic representation. How does G0 act. G0 is in the symplectic group. We take any of its prime images by the covering. So we have 2 points covering G0. And and any of these elements act by a Fourier transform on the function. So complex structure acts by Fourier transform. One must fix some points to get which one acts by plus Fourier, which one acts by negative Fourier, minus of the Fourier. Then differentiating the representation, evaluating in this J0 and plug that onto a function from Bargman-Fock space or from the Lagrangian picture space, we get just a Hamiltonian of the harmonic oscillator, which is also a remarkable property. And by actually using just that the metaplectic representation is a homomorphism, one can get for free that Hermitian functions are eigenvectors of the Fourier transforms. When Hermitian functions are just said to be all eigenvectors of this harmonic oscillator. And one can compute the eigenvalues consequently, which is another question a bit. So now to geometry. Symplectic, so we were in the flat case. Now we go to manifolds. So let us have a smooth symplectic manifold with symplectic form, in each point don't degenerate antisymmetric closed form. And let us denote the bundle. Okay, let's start with R of symplectic bases in each point of the manifold with respect to this symplectic vector space by R. On R, we can act by symplectic group from the right just by changing the database. This is a basis set of vectors, and the easiest way to think of it is to write the matrix from SG in omega 0 to the right and multiply by row times count, row times count, row times count, getting another row of vectors. And this will be again a symplectic basis, and this is a left, this is a right action. So, and now what is the analog of space structure? So this is what we do here. We would like to go to Dirac operators. So it will be a bundle P, which will be principal bundle for the double cover for metaplectic group, together with a map surjection of this bundle P into the bundle of this symplectic bases, symplectic frames, such that this lambda is almost bundle homomorphism, or principal bundle homomorphism. Why I say almost? Because we cannot actually we cannot, the structure groups are different. Here, the structure group is a symplectic group. Here, the structure group, the principal group, is a metaplectic group. So we shall demand this. So we will act on an element by an element from the metaplectic group B prime from the right. Then we take lambda. We shall go to R. And normally, I mean, when speaking about homomorphisms of principal bundles, we shall get the same as going from P to R and then acting by G. But G doesn't act, metaplectic group doesn't act on symplectic bundle of symplectic bases. So we shall use the covering, go from the metaplectic group to the symplectic group, and then act by this. Okay, I acted on this pointer, unfortunately, in the wrong direction. So this is the metaplectic structure. So this is actually this is fixed. Then by omega, it is a principle MP bundle, so for the metaplectic group, with almost homomorphisms of these bundles, meaning this. And so typically, the picture is this one. So this is what I mean. This shall commute, yeah. So it shall be a bundle homomorphism, meaning that the lambda cannot change the position of the frame. Commutes also this. These are projections on the point. Yeah, so you have symplectic basis in a point M, and it gives you this PR, gives you M, the point M. And here analogy. So existence is well known. Second Stiefel-Whitney class shall be 0 for the manifold, or first chain class of the complexified tangent bundle shall be 0. Shall be even. Should be in the image of even numbers inside. And the number of inequivalent classes, we can speak of this, what the equivalence between metaplectic structure is given by this cohomology, which can be nicely computed by universal coefficient theorem. So now we shall make spinor bundles. So and here symplectic spinor. Symplectic spinors associating the principal bundle and the representation together gives you smooth bundle of these spaces S. What were these S? As were these intersections, the smooth vectors. Okay. And one can take smooth sections. These can be called Schwarz symplectic spinor fields. For the bundle of Bargmann-Fock space, so we can associate also Bargmann-Fock. Bargmann-Fock is a representation space for the metaplectic representation, basically. But this bundle needn't be smooth. The canonical atlas needn't be smooth, and whenever P is non-trivial, it is not smooth. So I cannot speak about smooth sections. So we just declare the smooth sections to be smooth functions of the principal bundle with values in the vector space, Bargmann-Fock, which are G tilde equivariant. G tilde acts on P. P must be G tilde bundle, and it acts by the representation on what? On the Bargmann-Fock space. So this is declaration, so it's similar to what one knows as a result in the smooth case, fit very smooth. Quantization, so this is for you easy, symplectic manifold, smooth functions, function 1f defines a covector df, and one can take the dual, omega dual defined by this, a vector Hamiltonian vector field xf. Poisson bracket is defined by plugging into the Poisson vector for individual functions which you plug in the Poisson bracket. Quantization defined by Habermas, the quantization map, the homomorphism of three algebras. Take a function of the manifold, and you shall get a endomorphism of some, not Hilbert space, but here at least Fresher space. So let us take a section phi. So Q function here goes to here. Phi is from here, and one should get function again from here, section from here. One can take the derivative of this phi, multiply. So here I have some constants h, yes, so it can be chosen as 1 this h. And the result of Habermas and Klein is that the Poisson bracket satisfy this. So it is a quantization, Lie group homomorphism really up to a multiple. And so the problem was construction of the Lie derivative, but we will not go into it because we don't have time. But actually,
Is there any reason why you consider this almost determinants not time dependent?
not time dependent.
Yes.
Uh,
Is there any reason? Something
just analytical reason, because it's somehow simpler. The theory is simpler.
it looks like it will work. The time dependent.
Yes, but one loses some analytic features, yeah, but okay, which are known how to be recovered already. So for simplicity, let us consider this. Yeah, what is strange actually on this quantization? So first, we quantize on sections of some too big bundle. Why too big here? Consider the canonical case R2n. The shared space S, let's say some smooth vectors in L2L, so basically short space on L. And consider the trivial case when the bundle is trivial. So we have just functions on R2n, sections of this bundle, functions on R2n, I'm pointing in the wrong way, R2n into HBF or into the short space. So the space is too big. Normally you take just quantization of functions defined on Rn with values in R. And here you take functions on R2n with values in short space on Rn or L2 space or Rn or even HB or Barman-Fock space. So the space for quantization is unrealistically big. But nevertheless, okay, so these are just explanation what I said now. Smooth functions here. Hilbert writes it. So take L2 functions. And here don't take Schwarz, take the Barman-Fock or this L2 picture. But then this Hilbert, this square integrable functions on R2n with values in the Barman-Fock are isomorphic to this tensor product with completion. This is quite normal. This is infinite countable. So this is actually isomorphic unitarily to HBF only. So this is a remarkable properties of infinite dimensional Hilbert spaces that you cannot forget it somehow, one of the spaces. Yeah? In statistical physics, this is called compression. Statistical quantum field. Probably, but it's in mathematics, it's known for decades. And okay, so actually we obtain such a map, which is quite already classical. When you replace this HBF by L2L, you get just a map from functions, classical observables, into functions, into L2 functions, bounded operators on L2 functions. Problem, Q needn't be continuous and actually not bounded. I don't know whether one can write here bounded. So we omit many details, probably only densely defined and so on. So we omit analytic difficulties in this way. But we obtain homomorphism. Yeah? So analytical problems might appear, but this is miraculous because one didn't, there are so-called Grenewald-van Hout theorems which say that there is no non-trivial homomorphism satisfying this. That's, at least for me, why there can be a deformation quantization. Yeah, why one consider corrections of this strict homomorphism formula. So one cannot fulfill it, so one change it and one consider some perturbations. Okay. Yeah, but it doesn't contradict. Yeah, so we omit analytical difficulties, but the representation is not irreducible. Yeah, so there is a demand to make this, in the classical quantum theory, to make this representation of irreducible when restricted to functions to certain polynomials, for example, if it's n is R2 n polynomials, or to Heisenberg, or something above Heisenberg. But this is what one doesn't do in the deformation quantization to demand irreducibility at all, I think. Or I don't know it. So it is a nice attempt. Now the Diracs. We must take connections. This is necessary. Let us take a connection which preserve omega and is not has non-zero torsion. But even if we take zero torsion, there is infinitely many of connections. So it is not like Riemannian geometry, where there is only one, but there is a bunch of infinite dimensional. There's an infinite dimensional affine space model of the third pole of the cotangent bundle and section of it, which model the affine space of all symplectic connections. Then lift this connection to the bundle of symplectic frames and lift it to the bundle of the bundle P, which covers the bundle R, by the big lambda, metaplectic structure, and then associate it to the associated bundle of the symplectic spinor of the symplectic spinor bundle, and then you get a connection which acts on sections of this bundle. You get this. So this is standard in geometry, standard procedure. You cannot take this HBF because it is not smooth, so you take this short space. So short space times, we have this isomorphism pointwise in any point, because just this bundle is isomorphic to this by omega, the duality given by omega. We don't actually set the direction which the omega goes, but we plug it into the left-hand side. And EI will be identity times this duality. E2 will be identity times G. There is also G acting, take a Riemannian metric, for any compatible almost complex structure. And then you get your duality by G, and you have two isomorphisms. Non-trivial is existence of the almost complex structure compatible, but this is quite known in symplectic geometry that it might exist. That it exists. Okay, no modification. It can be proved that tensor product of the fiber, actually, of this Bargmann-Fock infinite dimensional times the tangent space in a point decomposes as a representation into the Bargmann-Fock again and some rest, which is a sum of two irreducible representations. The Bargmann-Fock itself is just two-step irreducible. It decomposes into two irreducible representations, and this rest decomposes in TBF as well. In two irreducible representations as well, inequivalent. Yeah, inequivalent. Okay, so we have this. Just we can consider projection. Just projection in a representation theory, or projection onto the direct sum. And this enables us to define first symplectic Dirac of Habermas and second symplectic Dirac, without speaking about the symplectic Clifford multiplication, which they very nicely introduce. But we can omit it by this representation theoretical decomposition. So we take the associated covariant derivative. It goes into this tensor product. Then we take E1. This is a identification in this way, this. And then we take P. Here we actually restrict this P to the smooth vector in the HBF, but it works as well. But some general procedures. And then we get two symplectic Diracs of Katharina Habermas, and also we can use her approach and define the associated operator by commutator of these symplectic Diracs. What is interesting? P is of second order, and its symbol is the metric G in point C an identity. So it is like a Laplacian in the case. One don't take anti-commutator as one could expect. These are first order operators. One take this anti-commutator. How to compute the spectrum on the sphere? It's a nice but technical. Sphere has good properties and the metaplectic structure exists. It's only one, so unfortunately it's trivial. So the metaplectic structure, the principal bundle for MP group is just a product.
So maybe you can continue for 10 more minutes.
Okay, thank you. The spectrum of P is given by this formula. This is achieved by representation theory using Casimir operators and some detailed computation. Depends on two numbers. For different LG, we can get same numbers, and even but above that, each number can have higher multiplicity, meaning that the vector of eigenspaces is more than one dimension. Can be more than one dimension. Yeah. At the end of the representation theory techniques, one finds Pell's equations, and one has to solve some specific Pell's equation connected to Archimedes' kettle problem. The kernel of P is infinite dimensional. This can be seen that the zero is achieved infinitely many times. This is connected to the Pell's equation. But P is not Fredholm, so it somehow put us out of the Fredholm picture. And here the formula for the numbers, so I omit it. Here's a spectrum. This is maybe the I and here is a J, or let me see it back. It's LJ. It's here probably L is J and J is here. I don't remember anymore. And here are the eigenvalues. Quite nice picture. Representation theory. Okay, so very briefly, we spoke about these tensor products. Why? Actually, no, let us go to the deRham. So here you have infinitesimal deRham. So only in the fibers or only in the tangent space. Yeah? So algebraic again. So we have 1 forms, 2 forms, 3 forms, 4 forms, dimension of manifold 6 forms, and we multiply by spinor. So we consider spinor valued exterior forms. So in gauge theories, we consider tangent bundle twisted by line bundles. And here we twist it by this infinite dimensional HBF or L2L. So we get just this row. And the spaces involved with respect to the metaplectic group needn't be this tensor product, these spaces, needn't be irreducible. And here are the decomposition. This symplectic spinors decomposes, it's technical like this, it decomposes like this, and this any element here is actually two-step irreducible. By this strange name, I mean that each decomposes into two irreducible spaces. So this is sum of two irreducibles. This as well. And moreover, they are inequivalent. So one forms are here. So this B times HBF was the smooth version. This decomposes into two irreducibles. So 4 irreducibles. So it makes such a nice shape. And okay, here is a GBT algebra of the metaplectic group. Let us choose a cartan. Let us choose we get a system of roots. Let us choose a system of positive ones. Then the fundamental weights are determined. They are denoted by variable pi. And any weight can be any weight in H star can be written in this way. Here is the triangular shape. So this parameter is the triangle. Here are the basic results. How these decomposes. How these spaces decomposes. We have such 1/2 weight. So it really reminds us to the spinor representations, from orthogonal groups and spin groups. There are also some 1/2. This is actually further analogy. Here are these EIs, how the weights are computed, and now here the decomposition result. There is a shape of it. Okay. So why not the whole deRham? And this is maybe why not the whole deRham in exterior forms listed by spinors? Because the differential operators, the deRham differential times the covariant derivative nabla s don't form a complex very often. For this big twisted complex sequence, deRham times nabla s to be a complex, needs nabla s to be flat and nabla to be flat, which is hard to achieve. Or I would like to get actually more complexes. Yes. For this reason, we can define smaller projections of the covariant derivatives onto some subparts, namely on these subparts, onto these subparts. These TIs, these projections of covariant derivatives, map this into this, this into this. They never maps into the all next possibilities. They map only into the one, into the extreme one. Just defining this way without changing the indices in the right way. The T's changes the index by 1, the left-hand side by 1, and this right-hand side index by 1 as well. These are called twistor operators or symplectic twistor operators. They are somehow analogical to the Riemannian case or to the Dolbeault case. Yeah? So they form a complex, not if the whole connection, if the curvature, the whole curvature of the connection on the manifold is 0, but only the veil part, the symplectic veil part is 0. This is the definition of the symplectic Weil tensor. So it's a mixture of some omegas and symplectic Ricci and so on. So you can omit it. And there are which manifolds admit actually connections which are not totally flat, but veil symplectic veil flat. These are specific bipolarized Lagrangian manifolds. Conditions are given by PDEs or by Pontryagin classes. Correia-Thurston manifold. And also, if the manifold is trivial, but nice, I mean, it has a compatible Keller structure, then if it is moreover geodesically complete, then it is known actually that it is covered by 3 types of manifolds already. So it is Keller and it is covered by 3 parts, 3 types of manifolds. Complex projective spaces, hyperbolic balls, and what next? Euclidean space. This canonical symplectic structures. Here I discuss whether the metaplectic structure exists on these Keller manifolds. It exists on all which are not covered by the even dimensional CP2K, but it's just a plane with pullbacks and factoriality of frequently and characteristic classes. So they are not only having a nice symplectically Weil flat connection, but they have also metaplectic structure. So for them, these complexes exist. Of TIs, this complex is 1, T00, T01, this is T10. So there are some indices. This is 1, this is 2nd, this is 3rd. This is false, but this complex has only 4 and 0. Only 1, not trivial, and here 0. Yeah, okay. The last slide says that these complexes are elliptic in the sense that the principal symbols of these three T's, of these twistors, are isomorphisms. Form an exact sequence. Yeah, the symbols of the Laplacians are isomorphisms. Also, definition classical shall be some quadratic form basically, but here we speak about fiber-wise about mapping. So the symbols are mapping between Hilbert spaces, between L2L into L2L. So the symbols are maps between Hilbert spaces already, because these are the fibers of the method. These are by which we twist. Yeah, so this can be proved that they are elliptic. Truncation means don't take too many zeros. So stop it here, don't continue with zeros, but I'm not sure about it. I just say it in this way, sorry. Truncated complexes of twistors, of these T's.
I'm sorry, so maybe, can you maybe just conclude the talk? Because
And then the last theorem is that this wedging by R is well defined on the cohomology of the twistors. And that's all.
Thank you.
Right, so thank you for the talk. And does anyone have any questions or comments? Maybe from the online audience? Oh, it doesn't seem that way. I guess we can thank the speaker again then.
Okay.
We will see everyone the next week.
Maybe